This is the video solution to problem 8-118 from the textbook. The problem reads, if P equals 900 newtons is applied to the handle of the bell crank, determine the maximum torque M the cone clutch can transmit. The coefficient of static friction at the contacting surface is mu s equals 0.3. So just looking at this problem, it's a machine frame problem combined with a friction problem. You can see that the hand is applying some force P, which will transmit a force to the shaft, causing pressure at the contact surfaces here and here. But keep in mind that this is a cone, and there is contact all around the surface of the cone. So to begin, let's just start with a force diagram of the lever. At point B, we have a pin joint, so there will be both a horizontal and vertical component of force there. At point A, we have P acting, and we know P is 900 newtons. Now at C, we only know that the force that is transmitted from point A through the lever to C is acting in the horizontal direction. We don't know the magnitude, so that is what we have to solve for. So we will use an equilibrium equation. Sum of the moments about point B equals 900 newtons times 0.375 minus FC times 0.2 meters equals 0. So we just solve for FC and find So again, this is the force that is transmitted through the shaft and applies force at the contacting surfaces between the clutch and the crank. So now we're just going to draw a separate free body diagram just for the clutch and the crank. And we know that the contacting surface of the clutch is at an angle of 15 degrees from the horizontal. There'll be some contact force along the surface. It will be like a distributed normal force along the surface, along the entire contacting surface. So since this is a cone, it would go around the radius. And also at point C, we have the force acting in the opposite direction as above in the lever diagram. Now there's several ways to solve for the normal force that is acting along the contact surfaces here. We are going to try and narrow the contact surface down to a single point along at a certain radius from the center axis, the axis of the shaft. So in order to do that, we are going to zoom in at the contacting surface of the clutch. And since this is a distributed normal force along the surface, we can approach this similarly to how we approach distributed load problems. So just draw a resultant normal force vector. And this acts at a point that is halfway along the distance of the surface. And there still is the force from C acting here. So now we have enough information to solve for the normal force. This normal force here represents the sum of all the normal force vectors that act at this particular radius right here, going all about the circumference of the clutch. So we just use an equilibrium equation. Sum of the forces in the x direction equals negative Fc minus Fn sine of 15 degrees equals 0. We have enough information to solve for the normal force. We find that the normal force is 6,520 newtons. We can also solve for the friction acting at this point. Just as with the normal force, this represents the sum of all the friction vectors acting along this radius from the central axis. And since we're solving for the maximum torque, we know this will represent the maximum friction. So we use the equation Fs equals mu s times the normal force. We were given mu s, so we just plug into the equation to solve for friction and find that the total friction is 1,956 newtons. So now we need to solve for the particular radius at which this normal force is applied. We know the inner radius is 0.125 meters. The outer radius is 0.15 meters. And since this resultant normal force and friction all act at this point, which is halfway up the surface of the contacting surface of the clutch, it is acting at the radius that corresponds to the average radius between the inner and outer radii of the clutch. So the average radius is 0.1375 meters. Now to solve for the torque M, we have to account for all of the moments about the central axis. So we know there is some torque M that is acting on the shaft, and friction is also providing a torque in the opposite direction. So these are the only two torques that are acting on this component of the machine. So now we use moment equilibrium equation. So sum of the moments equals the applied torque M minus the torque caused by the friction. So that is the total friction times the radius at which that friction acts. So we can find the moment by just plugging in the information that we've already found. And we find that the maximum applied torque M is 268.95 Newton meters. So this is our final answer.